My guest today is John Christy.
Well, I have a presentation about what I tell Congress, the courts, and my grandkids about climate change. And the first thing I tell them is climate change is not a crisis, even though they've heard everything. And I want to start with just one illustration of that. This is something that happened recently, especially in this part of the country. We had Hurricane Helene come and do some terrific damage in western North Carolina and eastern Tennessee with very heavy rains as the storm decayed right over the mountain range. And you saw headlines like this, that Helene was supercharged by ultra warm water made up 500 times more likely by global warming. Fire hose. Asheville's flood was because the experts agreed it was all climate change. Well, when you look at data, and this is what I try to train the graduate students here about, let's look at everyone's claim and go back and look at as much data as you can. And what you see here is 300 years of the French Broad River, the river that caused so much devastation. And to the right is in the past. And you can see that the flood levels for the first year, the years before 1880, were consistently higher than the ones after. Now, the big storm of 2024 is about the same as the one in 1769. And so, and you hear this other story about, well, the hurricanes are they're getting worse and so on. But if you look at the numbers that are very publicly available, you will find that the Northern Hemisphere hurricane intensity has actually been below average this year, quite a bit below average. And just in the North Atlantic, the one that we're concerned about mostly are just a little above average right now. So you cannot look at a data set like this and say, well, it's obviously increasing because of human emissions. And so a scientifically defensible headline would be, North Carolina flooding equals monster flood of 1769, but long-term trend shows reduced flood severity. Now, that would be something you could defend. But actually, the story is a little bit more interesting than that. It turns out that the TVA, the Tennessee Valley Authority, had a plan to halt or reduce flooding in the Tennessee Valley, especially the French Broad River Valley. And so they had a plan to build these flood control projects in the higher mountains around the French Broad River. But there was a fellow who didn't like that, named Jerry Bertain, I should say, Jerry Bertain. And he was able to organize a group that blocked TVA from going forward with their flood control projects. So if you're thinking about this what caused the devastation of Helene in North Carolina, you can say, well, people were living in the wrong place. They were too close to the rivers. Or you could say maybe Jerry Bertain had something to do with it, and he's responsible for at least part of the flooding and the devastation that occurred because he was the one who led the effort to stop all of these flood control projects from being built. So every time you see one of these disaster stories, you can look at it from many different angles and find different explanations for it, certainly different than that humans are the ones responsible in terms of emissions. So Helene flooding of the French Broad River was not unprecedented, and a plan to prevent such damages was actually thwarted 50 years ago. So what I do, and this is a section, the rest of it really is about data sets that I've worked on, because when you have a data set of climate variables, it allows you to test claims, ask questions, discover answers about climate change. And so the following are some examples of data sets I've been associated with or actually built completely from scratch by myself. Now, I'm going to put in here a quote from Nobel Prize physicist Richard Feynman. He said, give all of the information to help others to judge the value of your contribution, not just the information that leads to judgment in one particular direction or another. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment or data, it's wrong. And so I try to train graduate students to find as much data as possible to see how these claims pan out. So the first data set we'll look at are daily temperatures from Fresno, California. This is a place I grew up in, very familiar with what is going on with the weather there. And so I wrote a book. Is it getting hotter in Fresno or not? And that's me climbing up on the roof. When I was a kid, I used to measure the rain, which didn't happen often in Fresno. It's a desert, really. I could see the Sierra Nevadas in the distance with the snow-capped mountains, just beautiful. And I was from a kid, my passion was really the weather, as you will see here in a moment. Anyway, so here's a little bit of artwork from that book. We're putting together a long-term record of temperatures for a particular station is really tough. And it's like making sausages. You have to deal with the military records that were made early on. And so they have to be dealt with differently than regular records. You have to deal with the fact the weather stations moved. And so that's a weather station running away. And this is one of the more scientific things I had to deal with was a lot of weather stations early on were on top of buildings. And so this one happened to be 97 feet above the surface. But fortunately, there was an airport just 2 kilometers away that had ground level stations, good measurements there. And so what we found in the, for example, in the wintertime, that there was a lot of low fog in our valley. It happens all the time. And so that in the daytime, it would actually be warmer up higher in the above the fog than it would be down at the surface. So remember, we have an airport station on the ground and the official Weather Bureau station on a building. So we had parallel measurements. And so on the right, you can see the effect of that in the summertime, the surface temperature, the one down there on the ground level was very hot compared to the station above where it was nice and breezy and above all that concrete and so on. But in the wintertime, it was the opposite, where the daytime temperature was colder. The nighttime temperatures were always colder at the lower station. So the station up on top of the building was always warmer otherwise. And so you have to take into account these kinds of differences as you merge data from different stations to give a particular record. So this is the result. This is the final result. And you see here that the temperature, if you drew a trend line through there, it's almost zero. It's about 0.03 degrees centigrade per decade. So that's not much of a trend at all. Now, the last, from about 2013 to 2022, you see that peak there on the right. It was pretty warm back then, but overall, you see a trend that's really not different from zero. I pointed out there April 1967, the coldest monthly anomaly, the coldest departure from average. And I think we did a statistical analysis. It's supposed to happen once in 5,500 years, but that's just regular Gaussian statistics. But anyway, I point that out because I was there. In 1967, I was a teenager and I had my own weather station, and that is my April 1967 record. And it's not easy. It's not hard to convince people that I was really the mayor of Nerdville at this time. I was just one of those guys that was different because I loved the numbers. I loved the weather. I did everything for it. If you look carefully, you can see in 1/4 of an inch, I wrote 4 lines of weather information for that particular day. And if you go to the book that I wrote, you can see the translation of what is there that I wrote. Now, for the nighttime temperatures, however, you see this is dramatic warming, 7 degrees Fahrenheit over the 120 some odd years, 30 years. And that is a perfect signal of urbanization, how these urbanized places are being used, the temperatures from them are being used to tell us that the world is warming. And really all you're seeing is they're telling us that people have built up infrastructure around these particular stations. And so you saw the maximum temperature having virtually no increase because during the daytime, the sun comes out, it mixes up the air fully. And so the urbanization has much less effect in the daytime than it does at night, where you have this shallow layer that gets warmed by the surroundings. And here's just an example. So in 1924, you can see the street pattern there on the left. where there was a bit of infrastructure downtown and a little bit going northward. It was a small town at the time. On the right, you see a Google satellite photo or aerial photo, and it's just completely urbanized. And you can imagine that certainly has an impact on the thermometer that was registering temperatures there. In fact, here is the result. You see that the nighttime temperatures are 3 degrees C. That's about 6 degrees Fahrenheit warmer now than they were 120 years ago. The daytime temperatures, the urbanization has affected it, but it's about 1 to 2 degrees Fahrenheit or 1 degree C. It's still, though, comparable to the whole warming of the globe. You can see that taking out the temperature effect of the urban areas is a very important thing. And Roy Spencer and I are working on research on that right as I speak. Now let's go from Fresno to the conterminous U.S. So this is the 48 states. So I went to build a data set of the 1,218 USHCN, that's the United States Historical Climatology Network stations. NOAA did a lot of work back in the 1990s finding the best stations they could. And so I am actually building the data set backward in time to 1899 and forward in time, because almost half of these stations have closed. And so you have to have a parallel station with them that can carry on the record. And you can see I've got most of nearly all of the stations done. And the few others are just ones that were never digitized, or like in West Texas down there in the lower part, there just wasn't anybody there in 1899. Or the Florida Everglades down in South Florida, just no one lived in that part of the world to take measurements. But this is a hair-pulling exercise for a number of reasons. And one is this. If you go to the official websites of NOAA and ask for, I want to know the hottest temperature ever to occur in Newport, Oregon. And this is what you will get. You will get a listing of temperatures, the highest being 94 degrees back in 1980, 94 degrees Fahrenheit. I have dealt with these stations along the West Coast all my life. I know that was not right. And so I went to the original records on the right there, June 1925. And there you see a 100-degree reading Fahrenheit. That's 6 degrees hotter than what this what the federal site would tell you. So I look back at the federal data, the digitized data, and you will see that it's missing. That's the ACIS, the center column there on the left. It has an M, whereas the co-op, which comes from the right side, has a 100. And it turns out that the algorithm that NOAA uses doesn't like spikes in temperature. And so it tends to cancel them out, say, no, we shouldn't use this, even though it was very clear that this day was 100 degrees, had an east wind, and that's what happens on the coast of Oregon. When you have an east wind, you have compressional heating, and you get these spikes in temperature. And almost, I think about 100 of such temperatures were eliminated by this method. And there are other stations with the same problem, Tillamook, Oregon, Seaside, Oregon, and so on. So that left me concerned that if I want to study extreme temperatures, especially in the West Coast, I can't really trust what I get out of the algorithm massaged information there. And so I went and I actually went image by image and filled in the missings so that I would have a better record. I'm sure I didn't get every single one, but I've got a lot of them. And so this is a picture from 1899 to 2023 of when did, or how much of the country had their all-time record high or all-time record low temperatures. And you can see that in 1899, the United States had 23% of the country had its coldest record temperature. And that was the February 14th, around the Valentine's Day storm that came in that was just brutal in the eastern half of the country. Then in 1936, you can see 22% of the country had their hottest temperature ever, and that was just a brutal summer. But otherwise, not a whole lot happened. You see a little bit of spike there in 2021. That was the Northwest Pacific heat wave that we'll talk about here in a second. But anyway, that's the picture of when did the all-time records occur. And there's not a whole lot to write home about when you look at that and try to make a claim that all-time records are increasing. They certainly aren't in this part of the world. Now let's take a more robust measurement. Okay, there are 153 days in the summer from May through September. So each day has a record high temperature. And so I went and said, okay, when did those record high temperatures occur for each one of those 1,100 stations? And averaged them out to tell you how many days, how many record highs occurred in each one of these 5-year periods. And you can see that back there in the 30s, the United States had the most. That's the circle with the line. And there was a little bit of a peak here in the last 5 years. Now, for a place in the Southeast, where I'm from in Alabama and Georgia and so on, the blue lines, the blue bars you see are downward. We've had much hotter weather back in the 20s and 30s and 1950s than today. But look at the West Coast, and you will see they had their most in the last 5-year period. So some have hotter, some have cooler as we go along. Okay, next we have another more robust thing. This is the number of heat, what I call heat wave days. So this is a number of days that are in periods of at least 7 years, 7 days, 7 days in a row consecutive, in which the temperature exceeded the 90th percentile. Now, if it were 10 days, then it would be 10 days per year. So this tells you per decade how many heat wave days were there per station. The orange bars are for the country as a whole. And you see that the last 10 years, about average. In fact, the trend is actually downward if you look at it for heat wave days. But you see there that Idaho at the Pacific Northwest at the green line and the red line, California, Nevada on the west, had their most. So they're having their worst number of heat wave days in the past 10 years. But you look at the upper Midwest and the Ohio Valley here, you'll see they had their lowest number of heat wave days. And so as a result, it all averaged out. And that's why the last 10 years, the United States has had just an average number of heat wave days. Going a little further, some of the data sets I built, this is a data set of temperatures in Alabama that goes back to 1883. And I wanted to compare them with what climate model output states. So this is one of the ways you can test claims is say, okay, I'm going to look at the climate model output versus what the observations are showing since 1883. And we see here that the red, which is the observations for Alabama, actually show a declining trend. And no model was able to reproduce that. And so 100% of the models overpredict the warming, some by a lot. I also built data sets for, I lived in Kenya for a couple of years. I had a little weather station there. I taught physics and chemistry in high school. And I found there, this is published in the Journal of Applied Meteorology, I believe, Applied Climatology Meteorology. And we see for the minimum temperature, the orange colors there in the center, that means the nighttime temperatures are warming in Kenya. But on the right, you see the daytime temperatures are not. And that's another signal that around the world, we find the same thing, that the nighttime temperatures are warming. And so they shouldn't be used in any way to tell you about what the effect of greenhouse gases might be, because urbanization is affecting them. Also did the same thing for Uganda, next door to Kenya and Tanzania, and got the same story. Temperature maximums were not increasing, but the minimum were. Now, how does a station's hottest temperature in a given year compare with the expected value of the hottest day each year? Okay, now think about this. So suppose you live in a city, and on average, the hottest day, the single hottest day of the year is 100 degrees Fahrenheit. Well, let's go year by year and say, well, how does the hottest day of each year compare with that average, that 100? And so this is what we get for 1936. We see that the hottest day in 1936 in much of the country was over 15 degrees hotter than the typical hottest day. And there you see on the right the 2021, and it was really confined right to the Pacific Northwest, so that it was, and the eastern half of the country was actually cooler than the expected highest value in temperature. And that gives you a sense of why 1936 was just a standout year in terms of exceptional heat within the United States. And we haven't seen anything like that since. And so if you average up all of the stations in the country and geographically average them, this is what you get for the departure from your average expected hottest temperature. So people like to talk about extremes. So this is the departure from the hottest temperature. And you see an actual downward trend here in the United States that we do not have examples of more of these extremes occurring recently. This one concerns me greatly because this is the Tennessee Valley. So this is basically the state of Tennessee with northern Alabama, a bit of Kentucky and North Carolina and so on. And this is the same quantity for the minimum temperature. So this is the departure in each year of the coldest day relative to the expected value of the coldest day. 1899 is the worst. The average lowest temperature that year was 20 degrees colder than what you would expect Fahrenheit. 1985, it was about 19 degrees colder. In 2022-23, that winter, 2022-23, the last one there, you'll see it was about 6 degrees Fahrenheit lower. And the reason of great concern is that was the first time the Tennessee Valley initiated rolling blackouts. I was going out to run that morning. It was 1 degree above zero Fahrenheit, and I had all my gear on. I had never run that cold before. I wanted to see how it was, what it was like. And just as I was stepping out the door, the power went off. And so I didn't want to leave the house, not having power, not knowing what might happen. Well, I say that because that was TVA's first time to ever cut power. And yet you see at least 15 years prior to that when it was even worse. So what that says is the way the energy infrastructure of our country is going or has been built, that we are not capable of handling just modestly cold events like this one. And that's a very dangerous situation in which to be, especially for those at home who need electricity for survival aspects of their lives. So I hope that our energy infrastructure or electricity will be made more resilient to these kinds of things. And I fear that it's been the result of going for renewables, the wind and solar, which were not helpful in this particular day at all. In fact, if you look at the difference between 1899 and 2023, the one on the right caused the rolling blackouts. What would happen in the country if the one on the left occurred again, 1899? It would be a disaster. Now, we do have many more power sharing agreements now, so one utility can share power with another more readily. But as you look at 1899, you would see all of the utilities east of in the eastern part of the country would have been affected, and they would all be wanting everyone else's electricity. So that's a warning right there for the next cold air outbreak. What about rainfall? We hear a lot about rainfall, and we're told it's supposed to be getting worse in terms of heavy precipitation. And so I was asked to do some work out in California, and I built this data set of 29 stations along right at the west coast of the United States. And they have what they call atmospheric rivers, where a big slug of moisture comes in from the Hawaii and places like that with lots of moisture. And when it hits the coastline and the mountains there, it just dumps heavy rain. In fact, there should be one coming in this weekend, I think, to the West Coast. So when you have these big data sets, I built this data set from 1892 daily. So I have every single day built. And it took a lot of work because some of these stations have missing data. So I had to find a comparable station that would fill in. And what I have here on the chart is when did the heaviest 10 events occur for 14 days? So a 14-day event, I took the 10 heaviest, when did they occur for these different regions? And a 14-day event will be like 2 or 3 really hard atmospheric rivers that would cause tremendous flooding. And what you see here is that there was a big event in 1999. That's that peak at the right, but there's no real trend there at all. And so we don't find an increase in the amount of heavy rain events occurring in the west coast of California, that these atmospheric rivers are still just plowing in as they will. And then down in Southern California, they were worried also about the heavy rainfall events more specifically. And so these are the 5-day events. When did the 13 heaviest 5-day events occur since 1894? And they were all worried when I went there in 2023. Yes, it was last October. And when I showed them this, they were surprised because it turned out in the last 5 years, there were none. No events occurred in the past 5 years. And you can see that there is no trend at all there, that these stations in the Southern California region that would give a 5-day event would be one big atmospheric river. And so here it says that these events are not increasing in the last 130 years. Then I built the data set, and this was 150 years long for what I call the humid Southeast. And I didn't have time to draw a map around these, but if you know where Austin, Texas is, and New Orleans, Louisiana, Washington, D.C., or Key West, Florida, you kind of have where you are, southeastern humid United States. And so building that data set, I asked the question about heavy rainfall events. And these are the 5-day events again. So this would be like a hurricane that came through or some real big heavy event that lasted a few days. And you see there's something that looks like, well, at the end there are 2 or 3 5-year periods. It looks like they have more than all the others. And certainly that's what it looks like. And so I looked at that individually and found out that all of that increase occurred in the 4 most northeast stations. And it turned out from about Washington, D.C. and northward into the northeast New England and so on, there have been a few more tropical storms, not many, but a few more than usual that have dumped heavy rain. You take those out, and then you have really no trend at all in these heavy events. What about snowfall? Snowfall is a big deal, especially out west, because so much of their livelihood depends upon snowfall or the melting of snow in the spring and summer. And people don't realize this, but snowfall is actually the directly measured amount for most of the stations out west. What they usually did was they measured the snow and then divided by 10 and said, okay, that's how much water fell. That's how was the liquid equivalent. And so for many of these stations, you do not find directly measured snow rainfall. In other words, where they melt the snow and measure the liquid. They actually just divide it by 10. And I went through many stations where you would see a snowfall of 11 inches, and then you would see 1.1 inches for rainfall. They just divide it by 10. So using this metric, how much snow falls each day, I did this for stations in Washington, Oregon, and California. Published this. Tremendous amount of work was required because a lot of these stations did not have digitized records. So I had to go through the records, the paper records for these states, and one by one go through the stations and to get the snowfall and fill it in with thousands and thousands of snowfall measurements that are not recorded in the official archives. And this is what you get. So in the Washington Cascades, the mountains, there's no trend at all. There's heavy years, dry years, but no trend. Oregon, same thing. In California, if you look carefully enough, there's a slight downward trend. This record has 4 regions in the western slopes of the Sierra Nevada. So these are the western slopes that are facing the Pacific Ocean. So the storms come in and dump their snow on these mountain slopes. that downward trend is dependent upon only one of the regions. The other three regions don't really have a downward trend at all. And the most critical one for water in the Southern California region is the Southern Sierras. If you know where Yosemite is, it's the area from there southward in the Sierras. And there is just no trend at all in snowfall. In fact, the second highest amount of snowfall occurred in the 2022-2023 season. So people want to say that, snowfall is going away in the West. No, it's still falling just like it always has. And the snow melt is still coming down as it always has. And this is kind of a thought about drought. You hear out West, people are talking about a mega drought. And it just confounds me to think that someone would call a few dry years a mega drought. Well, on the right is a map of Fresno County, the mountains where I was from, and Cliff Lake. Cliff Lake's about 2,800 meters, 8,000 feet up. And if you look in Cliff Lake on the left, you will see a cross section. And the current lake level is up there at the top, and about 5 meters below are the roots of a tree, a drowned tree. That tree grew, we had radiocarbon dating, that tree grew from 1290 to 1340 Common Era, AD. Now, that kind of tree can't grow in wet ground, so we know that the water was below the root zone of that tree for those 50 years. These alpine lakes all along the Sierra have the same feature, that there are drowned trees. That tells you that about 800 years ago, 700 years ago, the droughts were mega droughts, that those lakes dried up to the extent that forests could grow on the lake bottoms. That's a mega drought. What we have today is not a mega drought because we see these lakes with water in them. But it does give you concern. I think it should. That tells you the kind of variability that Mother Nature can provide out west. And so a drought like that could come back. A real mega drought could come back, and that would be a big concern out west. So let's go to global atmospheric temperatures. Roy Spencer and I have been building this data set for 34 years now of the lower troposphere, the bulk of the atmosphere. That's where the heat energy of the atmosphere is retained. We had a really hot April. That's a global temperature of the April map. It was almost a degree C above average, and you see there on the bottom right the time series, month by month, of the anomaly. We've had a very unusual El Niño. This past year, the temperature went up like it usually does with an El Niño, but didn't go down. So it went up rapidly, stayed hot, but it did not go down. At least it hasn't yet. And we're all scratching our heads. Why is it continuing to be warm when the El Niño part is over? And it's primarily in the Northern Hemisphere, and the Northern Hemisphere land areas are just not cooling off. So one thought is there's been a drop in cloud cover that allows more sunlight to come in and heat up the atmosphere. Some people think that the volcano Hunga back in 2022 put stratospheric aerosols, which were water vapor, I should say, put stratospheric water vapor in play. And so that acted as a big greenhouse and heated up the atmosphere below. So there are conjectures about why the temperature hasn't fallen. It's pretty easy to explain why it rose, because that's what happens on all the El Niños. But why hasn't it fallen? That's another interesting question. But you wouldn't say it was carbon dioxide because it's so sudden. It's up. And so carbon dioxide doesn't work that way. Carbon dioxide has a very steady, very slow, minor forcing influence of, get this, less than 0.5% of what is actually forcing the planet. So if you look up, sunlight and atmospheric radiation coming down, it's about 500 watts per meter squared. About 2 of those are from the extra carbon dioxide. So you can see that carbon dioxide is a very small part of that huge amount of forcing that Mother Nature brings. So understanding the response of the climate system to extra greenhouse gases requires accounting for the number of joules in the atmosphere-ocean system. So joules are just a heat unit. So we're just trying to track how many heat units are in the atmosphere. So the bulk tropospheric temperature is a good one, good representation of this heat content because there's so much mass there. The full ocean temperature is another. So this is a paper we published a few years ago in which we demonstrated that the blue line there is the actual global temperature of the troposphere. The orangish line is the impact of the El Niños and La Niñas. That's the SST effect. You remove that, then you have this green line that has two big dips, one in 1982 and one in 1991. And that was when the El Chichon volcano and the Pinatubo volcano went off. And so if we take out the volcanic effect, then we have an almost straight line, and it's going up about 1/10 of a degree per decade, a very small impact. And so what the paper was proposing was that that's a indication of the greenhouse effect. If you assume all of that warming, every bit of it was due to extra greenhouse gases, it's about 1/10 of a degree per decade. And certainly nothing that would be remarkable in terms of changing climate. Now on the right, this is a vertical picture. So we start out at the surface on the left and it goes up to 50,000 feet on the right or so. The feet are on the right. And this is the trend in temperature at each one of those levels. The circles represent observations. The open circles, the solid circles represent 39 climate models. And I think you can see that the climate models are warming the atmosphere way too much. In fact, when you get up to the upper levels where it's most important to get it right, the models get it the most wrong, 2-3 times the warming rate that it has actually occurred. So this has been something we've pointed out since 1994, when Nature magazine used to allow publications about real science and criticisms of the greenhouse effect theory. They don't anymore. But this was the impact we showed in 1994. This is still the case today. The climate models just don't know how to let their atmosphere release heat. They keep it in too much. Let's go to the Pacific Northwest heat wave, June 2021. Can you guess where the heat wave was? This is a map of our global tropospheric temperature, and you see that big red spot. That spot, that anomaly, happened to be the hottest grid point in the entire record, 46 years now. It was the hottest single grid point. And that kind of tells you that it was an odd thing. Was it due to global warming? Well, look at the rest of the globe. Most of it was below average. So it wasn't a background warming that caused this single spot to get so hot. In fact, there's a time series of the single hottest grid, summer grid, from 1979 to 2023. And there you see that event in the Pacific Northwest just stands out as the hottest one. And there's virtually no trend in that either. In other words, the hottest grid at each one of those of the hemisphere has not increased in magnitude. There were some 10 degrees values even back in 1979 for the hottest grid, 10 degrees above average. Why are observations important? Well, I just have to repeat what I said before, what Richard Feynman said. Give all the information to help others to judge the value of your contribution, not just the information that leads to judgment in one particular direction or another. It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiment or data, it's wrong. I have a booklet that's free. If you can download it from my Alabama State Climate website, and it talks about how Alabama's climate has changed, but I get into the whole issue of climate change in general with information from the country as a whole in there. So it would be valuable for anyone who is interested in what is going on in the United States as well as in Alabama. We just don't have climate change here at all that we can find. Lord Kelvin said, all science is numbers. He actually said something like, if you can't measure something and express it as a number, you really don't know what you're talking about. Feelings don't matter here. In science, you have to measure something and have a number. Then you can talk about evidence. And here is some evidence I think that is very important to close this talk is, what have hydrocarbons brought to the world? Well, hydrocarbons are responsible for the fact poverty has fallen tremendously in the past 30 years. Hydrocarbons are responsible for the fact production and yield of cereal crops has really gone up to record highs almost every year. What's interesting about that chart too is if I show the land required has actually fallen some because we're just more efficient at growing these things, and plants love carbon dioxide, so they really are enjoying this extra CO2 we put back into the atmosphere. And I say put back into the atmosphere because 50, 60 million years ago, and so there were 3, 4, 5 times as much CO2. And what have hydrocarbons brought us? They brought us the ability to protect ourselves from the weather. And so you see there in the bottom left, the climate deaths have almost fallen to zero because we just know how to protect ourselves. We're not going to see 50,000 people in Bangladesh drown from a cyclone because Indiasat, there's a geostationary satellite there that monitors these hurricanes and warns everybody ahead of time. And so those days are past. And finally, in the bottom one, if you happen to think human life is valuable, then you would be very interested in the bottom right line. For as hydrocarbons go, so does the life expectancy. So if you can place value on a life year, hydrocarbons have been the biggest boon to humanity that we have ever seen because of these numbers that are shown here that are pretty hard to dispute. So with that last slide, I just really don't see a climate crisis. So thanks for listening.
Yeah, this is brilliant stuff. Thank you so much for doing this. A lot of people are going to love seeing this. I do have a few questions here. What do you think about this issue? Some people are talking about ghost stations, where stations may have been gone for 20 years. And are we still using model data for maybe decades at certain spots?
Yeah, when I mentioned the USHCN stations had many had closed, well, because they had a fairly long record, NOAA wants to continue their record. So if they don't have a station, they generate data from a model. I would say a model of statistical analysis with stations around about. That can be good. It can be bad. I prefer to go to a specific station nearby, calibrate it to the old one so that we get the right kind of variance and so on with the station. The problem with the NOAA aspect is that the urbanization has just infected many of these stations that are being used to generate the information for the missing station now. And we see that in the USHCN data, that the NOAA data does have this warming in it that's urban biased.
I'm curious, are you working at all with Willie Soon at all on UHI, or you're mostly working on your own without collaborating much with other folks?
Yeah, Roy and I like to do our stuff together, and we get therefore a very independent kind of result, and it's great. Then we can go back and look at the work Willie Soon has done, for example, and his colleagues, Connolly's and so on, say, oh my goodness, it agrees. And we did it independently.
Excellent. Okay. Is it still the case then that they talk about a warming hole in the Southeast, even going to 2024, that is it not just Alabama, but in the Southeast, there is still a hole, right?
Yes, it's really been consternation to the folks who want the world to warm up because, yes, we actually have a downward trending temperature trend here in the Southeast since the 1880s, and just refuses to cooperate with the view that the world should be warming.
And then there's this issue of heat waves are supposed to be increasing globally, maybe since 1920 or something. But I'm wondering, it was really hot in the U.S. in the 1930s. You showed in Africa, heat waves are not getting worse. Do you think there's some place in the world where heat waves are way worse now than they were in the 1930s? Because I have not seen that.
That's a good question. I don't know for certain, because if I were to do the problem, I would want to do it with station data. But what we have today are these gridded data sets that are built and are contaminated by all this urbanization and other kinds of things. And so I think they will, and they also use minimum temperatures. And minimum temperatures we know are warming because of the urbanization effect dramatically. And so when you include the minimum temperatures, you get these increase in heat wave days that is not reflective of Mother Nature, but it's reflective of the infrastructure built around the stations.
It's interesting about the whole minimum temperatures warming up because I hear people saying, oh, that proves that it's greenhouse gases because that's what's supposed to happen with greenhouse warming. It's supposed to not affect the maximum as much as the minimum. But do you think UHI is a bigger factor in those minimums warming, don't you?
Yes, and I would challenge the people who say that because I actually downloaded the model data, the climate model data for the United States that showed the minimum and maximum were rising together. Some models had the maximum warming faster than the minimum. Others had the minimum warming. But anyway, overall, it averaged out that the maximum min were rising at the same rate, not like what we see in the real data.
Okay. Do you think there's a big role for UAH data in keeping everybody honest? Like there's RSS trying to sell their story, and there's there's a NASA or NOAA selling a different story. Do you think you're helping
Well,
keeping people honest?
it, I was on National Academy panels, 20, 30 years ago, and that was one of our recommendations always is to have independent groups do this. Independent groups build these data sets, and so then you can compare and learn from each other. And we've learned a lot from the others. NOAA, for example, has followed our lead in using one of the satellites, NOAA 15, as a real baseline because it was a very stable satellite for a long time. And so that NOAA's satellite data agrees almost exactly with the UAH data, satellite data now. The others like RSS, I know where their problem is, and I've written to them about it, and I think they know it too, but they haven't gotten around to working that out. They're using NOAA 14 satellite, which was it was a drifting satellite that they did not that they weren't able to really correct for.
Do you think that we're getting some pretty good data about Arctic sea ice coverage using satellites, or how good is our data about the sea ice coverage that goes back 100 plus years?
That goes back 100 plus years. It's hard to say. I mean, there's hardly any observations before the satellite era. And in the first satellites, it was very difficult because the resolution wasn't that good. And it was real hard to tell the difference between ice and low clouds, because they're both white in those old satellite sensors. But I rely on the Rutgers Ice Lab. They have a pretty good snow cover map because snow is more on land, and so we have people that actually were out there looking at the snow and measuring it. And so I look at those snow cover maps. But yeah, the Arctic sea ice has declined quite a bit through, I think it was about 2007, and then has pretty much stayed the same.
So just to go over again a point you already made, that do you think what the temperature data up at 30,000 feet or 40,000 feet, do you think that's kind of the biggest refutal or rebuttal to the story that greenhouse gases are behaving the way we think they are?
Yes, I do, because at that elevation, that is an elevation which the greenhouse effect maximizes its potential. So you have these greenhouse gas molecules throughout the atmosphere, and so the accumulation of them in terms of how it interacts with the radiative properties of the photons that are going up there will show you if you've gotten the thermodynamics of the atmosphere right, the moist thermodynamics. If you get them right, you will see the trends that we have from observations. If you have a little bit, it only takes a small amount, too much water vapor or too many high-level clouds up there, you will get that extra warming. And that's apparently what is happening now. The models are just leaving too much water vapor up there.
So do you have a personal idea of what you think ECS is? If you had to guess, if we double CO2 from here and leave everything else exactly the same, what would you expect to see?
Well, that was my paper with the tropospheric effect, and that ECS came out to be about 1.6. Now, Royce Spencer did a completely different study using the ocean temperatures and so on. He came out with 1.8. So we think we're pretty close, and the climate is just not as sensitive. I think the IPC says, is it 2 to 4.5 now? or I think it's 2 to 4.5. So we're actually outside the range of the IPCC.
Aren't there still people at the high end that are saying 8 or something centigrade? I thought I've seen ridiculous numbers that are
Well,
really high.
I think what the IPCC did was to say, well, those ones that are so high, we don't even believe them. So like the Hadley Center model, 5.6, there are other models out there, 5.4, they just kind of said, this probably isn't right.
All right. I wanted to throw in one human interest thing about running in cold weather because I'm old enough back. I lived in Minnesota back in the 70s, and our thermometer said 40 below Fahrenheit back then. And I was out there running. So it really was cold back then. I haven't seen anything like that since then. But the 1970s it really did cool a lot, didn't it, from the 40s to the 70s?
Yes, it did. I lived in South Dakota in 1977, 78, that winter. My goodness, it was just, we had 38 days or something like that where the temperature never got above freezing. It was down in the below 20s. Yes, those 70s were terrible years. If they came back, one would wonder, is our energy system capable of handling that?
And they are coming back, aren't they? I guess we don't know what's happening next,
Mother
but why
Nature
not?
tends to do that,
Yeah.
yes.
Okay. All right. Wonderful. Any other points you want to make before we go ahead and wrap this one up?
No, I would just like to thank any viewers and listeners out there that they took the time to listen to us today.
All right. Thanks a lot. John Christy, I really appreciate what you're doing. Thanks for doing this.
Okay, my pleasure.
Talk to you later. Goodbye.